Hello, this is Professor Bond. So what I'd like to do now is I'd like to talk about some various topics related to the subtleties of continuity, differentiability. What does it mean for a derivative to exist? What's the actual relationship between continuity and intermediate value theorem? Is it all the same? Is it all as easy as we think that it is? Or are there some, well, we're going to find out there are actually some pretty weird surprises lurking under the hood. So we're going to start with some stuff that's familiar, but we want to do it kind of a little bit carefully. So we're gonna see here that continuity and differentiability, well, there are some sort of surprises sort of lurking in the shadows. So we're starting with a function that's like differentiable most of the time. This is kind of a familiar fact, and we're just going to review it real quick because I want to really make sure we nail the particulars because there's going to be a lot of subtleties. So this is like a warm up, if you wish. So what happens? Is this function differentiable all the time, or is at this one particular point is it undefined? Whenever you're on an edge case, well, you have to bust out the definition and just do it manually. So maybe it's a number, maybe it's undefined. At 0. Well, let's find out. So we kind of know that this function on an open interval to the right of 0, it agrees with the function x. So the derivative is just 1. To the left of 0, it's -1, but right at that endpoint in between, well, really annoying stuff happens. Let's find out. Okay, so if f prime of 0 exists, then f prime of 0 equals limit as x approaches 0 from the right of f of x minus f of 0 all over x minus 0. While the absolute value function, if x is approaching 0 from the right, then that's just x over x. Limit x approaches 0 from the right, which is 1. But on the other hand, but also f prime of 0 is equal to limit as x approaches. So if f prime of 0 exists, if it's equal to anything, it has to be 1, because here we take the limit from the right, the slopes are all equal to 1. But on the other hand, we get this. So if x approaches 0 from the left, then the limit as x approaches 0 from the left of that same difference quotient. Well, the absolute value function, if we sample x values that are negative, then the absolute value of a negative number is the negative of that. So x, so it's just minus x divided by the denominator is still just plain old x. Limit as x approaches 0 from the left. So that's a contradiction. prime of 0, therefore does not exist. So great, that's for starters. So what is this saying? F prime not only is the derivative, you know, this we can't just do this and call it a day. If we're doing that, we would have to mean something very informal, just kind of hand wavy. We'd have to make up some new, you know, sure, the average of the limit from the left and the limit from the right is 0, but that's not actually the derivative in the sense of a two-sided limit existing. So that's just nothing. So the derivative fails to be continuous. And we conclude, well, well, in this case, the derivative at that discontinuity is not a defined quantity. So, so here's a question that it's not as obvious as you think. This one little bit of anecdotal evidence might lead you to think one thing or another about it. And so, well, this one particular case, in this case, the derivative, we approach 0, a equals 0 from the left and from the right. We get two different limits. It turns out that, so the limit fails to exist. So if the limit fails to exist, does the derivative itself fail to exist? And that's what we're going to look at next. So it's going to get, so this was just kind of a warm up. It's going to get kind of weird from here. So what we want to do is we want to take a closer look at continuity, and we want to take a closer look at the derivative. We're going to use the definition with some more mature examples later. And we're going to see whether this is true or not. If it's not true, can we say something kind of related? So that's going to be, we're going to have some examples, and we're going to have this thing called Darboux's theorem. All right, so here's a function that I want us to look at, and I want to investigate whether or not this graph, I'm graphing sine of 1 over x, and I want to investigate what some sample points are doing. 1 over x is a function that blows up as x approaches 0. But instead of shooting off to infinity, we're taking sine of that. So if sine of a real number can only go between -1 and 1, so you can think of 1 over x as being theta. So we're taking sine of theta. We do something very similar with cosine. We'd get the same thing, but kind of, you know, the angles are all displaced a little bit. So what happens? Well, if theta is 1 over x, then as x approaches infinity, theta approaches 0. And then sine of theta is like sine of a small positive angle is something that goes down to 0. And then we go, as x decreases, then theta increases. Eventually theta is pi over 2 when x is 2 over pi. So you could pause the video and you can look at this very slowly to sort of verify that these few things I did just to get us started are all correct. And so it's 0, 1, 0, minus 1, 0, 1. It's just an infinite sequence of angles are compressed and in backward order. So we go around the units. So theta goes around the unit circle once, and then twice, and then more and more and more. If you were to zoom in on this, you can use Desmos, is the really popular graphing software. where you can just type things in on a computer and it'll tell you. You can see it in more detail, but yeah, just it's as x decreases, theta increases. So you've got a bunch of sine waves that are getting smaller and smaller and smaller, and everything that sine ever does is packed into this little singularity around 1 over x. So it's pretty wild. But what we want to do is we want to see how does this function, what happens at 0. And this is going to be, I just want to talk about it, continuity versus the intermediate value property. And I want to apply that to the derivative of some other function. So you could ask yourself, ooh, what kind of function would have this as its derivative? If I took an antiderivative, and I've got lots of ups and downs that are canceling each other, it's pretty weird. But anyways, intermediate value property. So a function that has an intermediate value property is one such that if you have a less than b, those are your two inputs, and then g of a is less than g of b. And if you also have a number, lambda, in between g of a and g of b, then there always exists an x value between a and b such that g of x is equal to that intermediate value. So this particular function, well, I gave it a special definition. I plugged in, it's undefined when x is 0 because we're trying to take sine of an undefined, but I just defined the function just to be 0 just for the sake of argument. It's sort of halfway in between the two things that it wants to be, so I'm going to call it 0. Is not continuous at x equals 0, but these are the two claims. So I claim that it's not continuous at x equals 0. So what happens when you try to take a limit as x approaches 0? Well, the function gets close. The function is equal to 0 infinitely often, but it's also, it doesn't settle down. It never stays here. It's no matter how close you get to the origin, it's always jumping up to +1 and -1. So it's inconsistent. So it's sure, it visits infinitely often, but it doesn't stay there. So for a limit to exist, it's not allowed to, you have to get close and you're not allowed to leave. So it fails, the limit fails to exist. So that's this statement. So sine of 1 over x is not continuous. Similarly for cosine, it's the same thing, just sort of all, kind of shifted over left or to the right a bit. But it does have the intermediate value property. Why? Well, okay, so I claim that, well, if you take anything that doesn't include the singularity, let's just talk about the right half. So for the right half, you have this point at 0, and if I call this one a, and for the sake of argument, let's say I have a point b here. Well, for convenience, what I would like to do is I want to prove this function has the intermediate value property. I can just use the plain old intermediate value theorem just by I've got an infinite sequence of zeros, and as soon as I pick a 0 that's to the left of b, I can apply the intermediate value theorem to this interval. So I pick one of the zeros that's to the left of b. So I want somewhere in between 0 and b. I want to attain. Let's say I want to find a value lambda equals 1/2, for example, and let's say this is y is equal to 2/3. So I would like to hit the value somewhere in between. So what I do is I pick another 0, and I use the intermediate value theorem on this one right here. So let's say, you know, yeah, so let's say we plug in 1/3 pi for x, sine 1/x is equal to 0. Well, the intermediate value theorem applied to this function. Well, if I'm to the left, or if I'm away from the singularity, then the usual intermediate value theorem applies to this interval, which means that there has to be something like this, or maybe this one. There could be more than one, but here we go. There's going to be some input such that the output is lambda. So yeah, that one's pretty wild. There's a ton of random oscillation, but you just sort of, in this example, we know that we're going up and down. We're on both sides of this point infinitely often. If we just pick something that, if we pick another 0, then we use intermediate value theorem on this nice piece where we cut off the singularity. And so so how far do we have to go? It depends. Well, if B was here, then we'd have to get even closer to the origin, but then we're still good. So this is something to keep in mind. So usually it's not super duper important for applications to look at this, but it's good to know that this stuff is out there. Continuity. So if it's a Venn diagram, it looks like this. So sine of 1/x is one example where you have the intermediate value property, but you're not continuous. So f has intermediate value property. If you're continuous, then you're automatically having the intermediate value property. But they're not literally the same thing, because you can have intermediate value property but not quite be continuous everywhere. Yeah, so you could ask more advanced questions like how big can a set of discontinuities be for a function that still has intermediate value property. You could do all kinds of crazy stuff. But let's just keep going. All right, so where we're going with this is, the original question was, well, can a derivative behave in this manner? Okay, so let's start erasing. So we're going to try maybe a couple of things before we do everything. I want to get us a little bit more practice with this. So can a derivative have the intermediate value property exist, but exist at a weird point where the derivative fails to be continuous? Let's try this first. Well, this by the squeeze theorem, it's between x and minus x, so definitely the limit of the function itself is 0, so that's how you plug in the singularity, but we actually get something that's differentiable when we do this. I don't want to spend as much time on this one, but here are the two. So it's Crazy Town near the singularity, and then eventually it does something like that. Actually, this is an even function, isn't it? Because it's an odd function times an odd function, so something like that. Okay, so I didn't make that look quite as odd as I should have, or even, so. Okay, that should have been it's nice and symmetric. It's closer now. But, and what happens is actually, I'm just going to sketch it geometrically. You can do a formal proof. It takes a lot longer, but what you do is you get sample points that get closer and closer to the origin. That slope is -1, but then you also get upper sample points. So that sequence that we started with at the very beginning, when sine of 1 over x is 1, x times sine over x is on this line at these sample points. And then when sine of 1 over x is -1, we end up on this bottom line where the slopes of those secant lines infinitely often. So for infinitely often as the sample points approach 0 from the right, and the secant lines, infinitely often the secant lines have slope +1 as x approaches 0 from the right, but you take different sample points. So you don't have to worry about this too much, but if you know what this means, then now's a good time to refresh. Lim sup and lim inf. So there are a few different equivalent definitions of this, but lim sup means you approach 0, but you take a sequence that, and then you try to maximize, how big can how big can this expression be infinitely often as you approach the origin. No matter how big you pick your sequence, you're never going to get bigger than 1, but you can get as close to 1 as you like. That's called the lim sup. And if I cleverly pick my sequence to make this result as small as possible, then I approach again from, in this case, I'm still approaching from the right. If I pick my sample sequence to get the smallest number possible, that's called lim inf. And you get -1, and if these two numbers agree, then it's just called a limit, because no matter what, you get the same thing. If they disagree, then the limit just doesn't exist. Okay. All right, so that was just a kind of a warm-up. So we didn't quite get there. We want the derivative to exist, but we want the derivative to fail to be continuous. Is there a way that we can do this? And that wasn't it, but this is something you want to keep in mind. We're going to see, this is going to make a reappearance. I did kind of a graphical exploration of it. You could do it numerically as well. Like the x, like this x cancels that x because you plug that in for f of x. Then the sign of 1 over x that's left over is infinitely often plus or minus 1. So everything you need was right there on the board. It's YouTube, so you can rewind if you want to rewind and pause and compute it. I claimed that was a step in the right direction, but we're not quite there yet. Now let's try something else. And again, clearly, if you're good at Calc 1, it's but what happens, this is between, we have something that's between minus 1 and 1, and we have the function, so we have, it's between, the whole thing's in between plus or minus x squared. Either way it approaches 0. That's a quick sketch. So we have these kind of guidelines. Y equals x squared. We have y equals minus x squared. Ooh, what's going to happen at that? It looks like no matter what we do, yeah, something like that. Except now it's going to be an odd function. Because it's even function times an odd function is another odd function. So something like that. Okay, so it doesn't have to be perfect, but this looks a lot more promising. And then we plug in the whole by saying f of 0 is equal to 0. That looks really flat to me. Like before, it was between two diagonal lines, and it hit the two diagonal lines. If it's hitting two parabolas, it gets squashed. So this looks a lot better. Well, the really interesting thing is f prime of x. So 2x, so it's the product rule, so we differentiate the first one. And then we add x squared times differentiate the outside function. Okay, so yeah, maybe you're rusty. We differentiate one, we differentiate the other. So now we're differentiating the second one. The first time we differentiate the first one. So what do we get? We differentiate the outside function. But then that cosine, or that sine function there's an inside function. We do the chain rule, we get negative x squared, or negative x to the minus 2. So we get 2x times sine of 1 over x. We have minus, just one minus, so it's the whole thing is negative at the end. Okay, so the question was, what happens in the limit as x approaches 0 of f prime of x? Does this even exist at all? So this first term, that limit is just 0 because it's a good old squeeze theorem. Sine of x is between -1 and 1. So if you have something that's that's just between -1 and 1 multiplied by something that's approaching 0, this term is basically gone in the limit. But this we have something that's going to 0, but we're adding something that again, we looked at the graph earlier. We saw that this thing right here, cosine of 1 over x, retains all values infinitely often. It retains all values infinitely often as x approaches 0 from either the right or the left. So if we blew up this picture, so we blew up this little picture right here, we would have, maybe the function would have a tangent line like this, and then it would have a tangent line like that. Those tangent lines infinitely often, no matter how close you got to the origin. If you go just a little bit to the right of the origin, and you look at like one pseudo period of this cosine 1 over x thing, you would get lots of diagonal lines that have slopes approximately plus or minus 1. So the derivative, it's going up with slope 1, it's going down with slope -1, back and forth, back and forth, back and forth. But what happens exactly at the origin? The origin sees two parabolas. Everything's squeezed between two parabolas. It's got nowhere to go, but as soon as you get away from the origin, it's vibrating up and down very, very fast. So, yeah, so that's, I want to this is what I wanted to keep from that discussion. There are two different questions. Does the limit exist as x approaches 0 of f prime of x? And does f prime of 0 exist? And that's the second question. And I claim you shouldn't jump to conclusions. The conclusion is not that f prime of 0 does not exist. The limit as x approaches 0 of f prime of x does not exist. We literally took this expression where x is not equal to 0, and we took the limit as x approaches 0. We saw that expression keeps bouncing between plus or minus 1. And let's do this. So I claim that we're squeezed between two parabolas, so we're going to get 0. But let's prove it. So f prime of 0 equals, if this limit exists, the limit as x approaches 0, f of x minus f of 0 all over x minus 0. Limit as x approaches 0 of so the original, we want to see the derivative of the original function of f. So that's x squared sine 1 over x minus, well, f of 0 was defined to be 0, because that removes the singularity, or that plugs in the hole. And the whole thing divided by x. So we've got x times sine of 1 over x. And this is one reason we studied this one earlier. This expression here, that's the removable singularity. That limit is There it is, the difference quotient of the function f of x equals x squared sine of 1 over x is, so f prime of 0 is 0. So that's something, that was the central example. That's where all this was going. So I wanted you to see there's only one, so you could just do the product rule and the chain rule for any x value other than 0. There's only one point that could have possibly been a problem, and this was it. Well, you don't just give up and say it doesn't exist. We simplified this a bit as well. So sorry, the x squared and then the minus x to the minus 2. Okay, that's simplified form. Okay, so this expression, this is a discontinuous expression, but so the limit of this expression as x approaches 0 does not exist, but f prime of 0 nevertheless does exist and is equal to 0. So you don't just say that the limit doesn't exist and you call it quits. You just go straight back to the definition, like the very first day of derivatives in calculus 1. Just do the difference quotient. Does that limit exist? And yeah, we got it. Okay, so again, get some wild oscillating behavior, and the actual value of f prime of 0 was nice. It was nice right there in the middle. It's just like the sine of 1 over x example. You're here. As you approach 0, you're all over the place, and you've got the intermediate value property. So that's where this is headed. Okay, so all right, so let's just do a quick. So finally, I want to tell you what Darboux's theorem says, and then I want to show you how various things relate to each other. And what's what? So this is some guy's name. It's a French word. So my French, I don't actually know French, but I looked it up. And Darboux is basically the closest thing to me pronouncing it correctly, even though there are some subtleties to how you pronounce words. It's sort of halfway in between Darboux and Darboux is the closest thing that I was able to find. I was listening to a few different examples where they're trying to tell you how to pronounce it. Got mixed results, but everything was sort of a sliding scale between Darboux and Darboux. So it's kind of like you do something weird with the R that I'm not a native speaker, so I had trouble with it. But anyway, Okay, so that's the Darboux's theorem. So, quick remark. It's okay if the derivative at a is you take the limit from the right of the difference quotient, because as far as we're concerned, the function doesn't even exist to the left of a. And the same thing at b. You take the limit as x approaches b from the left of the difference quotient. If those one-sided limits on the endpoints, similar for how one-sided continuity would be defined, then that's good enough to guarantee that Darboux's theorem is satisfied. So I just want to verify that the theorem is true. So the conclusion that we want to show that the intermediate value property is satisfied. Well, this one, no, the intermediate value property is not satisfied, but that's okay because the function itself fails to be differentiable in a, well, sure, if you take just, if you let a equal 0, then the right half is totally fine. If you take the interval from -1 to 1, then it's not fine because there's then x equals 0 is an interior point. So this is false. So if the premise is not true, you don't need the conclusion to be true. There's nothing to show. What we need is if the function is differentiable in the entire interval, we better have the intermediate value property. This is an example that we looked at earlier. X times sine of 1 over x. The slopes approach plus or minus 1 as x approaches 0, but it wobbles back and forth. So both of these are examples like this. So sure, if the derivative happens to be continuous like all of our favorite functions from Calculus 1, then the intermediate value property is the conclusion of the intermediate value theorem. So the derivative is a continuous function on the entire, on any interval that you choose to investigate. So f prime is continuous, therefore f prime has an intermediate value property. So the one that's really interesting though is the one that we just did. So this is f prime at 0 exists. F prime is not continuous at x equals 0. And by sort of some similar arguments, well, sine of 1 over x has intermediate value property. By very similar arguments, that f prime function, the derivative of this function, and then you plug in 0 at 0, that derivative, that resulting function does have the intermediate value property. Very similar argument to what we did with just the plain old sine of 1 over x function. Let's sort of let's just prove one case of Darboux's theorem. Well, we're going to prove the theorem, and it's just like basically there are two cases that cover everything, and they're very, very similar, and it's just very routine. Once you prove one case, you have the overall idea, and then everything else is just you just sort of take vertical reflections and draw the same picture again, and then you repeat the same argument, but flipped over on its head. Okay, so I just erased the statement, but I want to do case 1, which is basically and again, at A and B, we only require one-sided derivatives to exist. For the sake of the argument, they're just because lambda is in between the two. So f prime of A, I'm just saying for the sake of argument, we would have to repeat the argument. If it's the other way around, we repeat the argument, but with changing everything that needs to be changed. So if we pick a number in between f prime of A and f prime of B, then there exists an x in the interval from A to B such that f prime of x is equal to the intermediate value lambda. Okay, so we've got A, we've got B. So f prime of A, they could both be positive, they could both be negative, and the argument's going to still work. But I'm going to draw two positive slopes. So this one's steeper, this one's a little bit shallower. So we can do that. All right. So that's what the picture looks like. I think strict inequality is the way this is usually stated. Okay, so let's do the proof. Let's call this f of x f prime of A, we've got f prime of B, and then we have some intermediate slope lambda that's in between the two slopes. So we have an intermediate value for the slope that we want to attain at some right. Okay, so this is very similar to if you know how you use Rolle's theorem. It's a special case of the mean value theorem, and you subtract a constant times x to transform the problem into one where suddenly everything looks more obvious. So what happens here is I'm going to call this, okay, yeah, so y is equal to h of x. What you have is you have a positive slope here, and now what's special about this is that you get a negative slope over here. And what you want is so here's the special value x here, that's what we're looking for. So that's what's kind of groovy about this. So this is h prime of x. The whole utility of h is that h is a special function such that h prime of x is 0 if and only if f prime of x is equal to lambda, which is what we want. So all we have to do is we have a function that's increasing as you exit A, and then it's decreasing as you enter B. Well, where is the slope going to be 0? Oh, that's going to be relative max. So that's really it. Not f. Now we're looking at the utility function h. If we do that, then we are done. So h has differentiability, and one-sided differentiability on the endpoints, which implies that h is continuous with one-sided continuity at the endpoints. So h is continuous on A to B. I believe this is called the extreme value theorem. Implies that h attains a global maximum on its domain. So why is it nice that we have the slope being positive and then negative? Well, h of A, we could be a little bit more rigorous with epsilons and deltas if this is like homework for a college course, but I just want to give you the idea. You can prove that h of the maximum can't be at x equals A because this function is sloping positively, so the difference quotients are all positive in a small interval, which means that the function is greater than h of A for all inputs that are just a little bit bigger than A. So with absolute extrema, you have to be careful because there's one of two things can happen. The endpoints, the maximum can be on the boundary, or the derivative can be 0. When we really, really want the derivative to be 0, because then we're done. We've won the game. So it's, we have only two boundary points to consider because it's one-dimensional. At some input value, which we can call x. So if it's on the interior, the derivative has to be 0. So one of two things happens: the maximum can be on one of the boundary points, or the absolute maximum can be at the interior. If the maximum is on the interior, the slope can't be positive, can't be negative. It's either 0 or undefined. Well, the hypothesis of the theorem is that the derivative is defined, so it has to be 0. Okay, so that was a lot. So yeah, let's just sort of summarize everything. So Darboux's theorem basically says, no, if the derivative exists on the entire interval, it doesn't have to be continuous. It does have to be this sort of almost continuous. For many purposes, it might be as good as continuous, but not for all purposes. So you have to be sort of careful about that. In particular, you're going to satisfy the intermediate value property. All right, so I think I'm gonna say a couple more things without proof. It's getting a little bit long. Maybe you can fight it out in the comments. I was just sort of looking at this as I proved it, but it's not quite. I don't really want to go into detail, but I do want to say these things. This is just a true statement. It does require some proof. You might want to draw a picture and think about it some. But if the one-sided limit exists, and you pick a point within that interval, let's say the left end point, because we want to use the letter A here. I think I'm going to use C because I want to consider left and right. If there's a limit as you go from the left, and if that limit exists, and your function has the intermediate value property, then g of c is also equal to L. Okay, so all right, so this is what this last example is what the absolute value example looks like. So f prime is equal to 1, f prime is equal to -1. You've got the derivative has two different one-sided limits. And if the function were differentiable at 0, then the function would have the intermediate value property. But if the limits disagree, then the derivative itself just cannot exist whatsoever at that point of disagreement. So that would contradict Darboux's theorem, because if this is what f prime is doing, then so no matter what f prime of 0 is supposed to be, it's not attaining every single value in between. So you can't just plug this in and call it a day, because it's not attaining the intermediate values. That's the contradiction right here. So some kinds of discontinuities are possible. Other kinds of discontinuities are within the realm of possibility. So jump discontinuities, where the two limits disagree. Darboux theorem says that this kind of discontinuity is impossible, but the example we saw earlier this function, on the other hand, has that derivative is discontinuous, but it's okay because it's not in this scenario right here. So two examples to compare and contrast. Why do some discontinuities make it impossible for f prime of 0 to exist? Why do other discontinuities Nevertheless, f prime of 0 is well defined. Why is that? Perfectly valid. It's kind of deep, but we had to analyze all those examples separately. Different things happened. Darboux's theorems is kind of overkill. You know, sure, you would just do this manually. You would see that f prime of 0 does not exist, but Darboux's theorem is a big fancy tool that sort of lets you assert sort of theoretically, this is f prime of x. If f prime of 0 exists, then we fail to have the intermediate value property. Therefore, f prime of 0 is just, nope, can't possibly, you can't possibly resolve that. It's just pure nonsense. So that was it. That was it's kind of a lot, but it's sort of basically this is the kind of stuff that you would look at if you take a college class in proof-based calculus. Sometimes they call it advanced calculus. Sometimes they call it real analysis 1. Usually what they would do is they would prove Darboux's theorem. They might spend 10 minutes just sort of telling you what the example is. And then maybe they'll give you like a couple of homework problems and you would have to figure it all out yourself. I did some stuff in a little bit more detail. I made a couple of assertions here. And these are all things that you could prove if you had to. If you, well, depends on how good you are at proofs, but you can fight it out in the comments if you're so inclined to sort of pick at some of these details here. But that's plenty. So that, as a wise man once said, that's a good place to stop.